This is Rosen, Discrete Mathematics and its Applications, Section 13.1. Continue our discussion of formal languages, and we turn to language generation. If I've got a phrase structure grammar G, I say that the language generated by G is a set of all strings of terminals that are derivable from the starting state. It's denoted L of G. I can represent it as a set, so all the strings W that are an element of the set of all possible strings over my terminal vocabulary, such that from my starting symbol I can produce W. Here I have a small phrase structure grammar, non-terminal symbols S and A, terminal symbols A and B, identified here, start symbol S, and productions. S produces lowercase a, uppercase a, S produces lowercase b, A produces lowercase a. And the language for this grammar is nothing other than B and AAA, because those are all that I can derive from these production rules. All right, what about this language here? I have a set 0 to the n, 1 to the n for n non-negative. That means I've got a concatenation of n zeros followed by n ones. And how can I create a grammar that creates that? Well, I know I need a 0 and a 1 in my vocabulary, in my terminal vocabulary. And I just need an S in my non-terminal vocabulary. And the starting symbol is S, and that's typical and even usual. Here's my productions. S produces 0, S1, then S produces lambda. And I apply that any number of times, as many times as needed, n times, to get 0 to the n, 1 to the n. But I have to be able to get rid of that S, and this S produces the empty string allows that. And again, the empty string is not a member of the vocabulary because it is not something you can use to build a word. It just represents the string of 0 length. Okay. Let's take a look at this one. This is 0 to the m1 to the n. And I'm going to show two grammars that produce 0 to the m1 to the n. That is, concatenation of m zeros and 1 n's. M and n don't have to be equal, and either one of them can be 0 or both. So I'm going to talk about grammar 1. My obvious symbols I need. I'm going to have S produces 0S, S produces S1, S produces lambda. So basically, it's very similar to the other one where I just keep producing zeros by application of this rule. Then I just keep producing ones by application of that rule. And when I want to be done, I apply the empty string. Okay, so that's fairly straightforward, but here's another grammar that produces the same alphabet, or the same language. And now we have S produces 0S, S produces 1A, S produces 1. A produces 1A, A produces 1, and S produces lambda. What this does is it builds up the word from the right, moving left to right. Just like you write a word on a page, you write from left to right. This builds up words left to right. And it turns out that this type of grammar up here is type 2, and this grammar down here is type 3. Even though they do the same thing, you can see this is a little bit more complicated because it has the restriction that non-terminal symbols only on the left, and all production rules result in either a terminal symbol or a terminal symbol followed by a non-terminal symbol. All right, here's an even more complicated language, 0 to the n, 1 to the n, 2 to the n. And we have production rules here. There's an error here. This needs to be a C. So S produces C, C produces 0 CAB, to stop the production, put C equal lambda. Then have this B equal B is produces BA produces AB, 0A produces 0, 1, 1A produces 1, 1, 1B produces 1, 2, and 2B produces 2, 2. Okay, so let's generate 0 to the third, 1 to the third, 2 to the third. So I know I'm going to apply this 3 times. So I have S, C, 0, C, A, B, 0, 0, C, A, B, A, B, 0, 0, 0, C, A, B, A, B, A, B. And then I'll get rid of the C using that command there. So 0, 0, 0, A, B, B, A, B. Now I can look at other things I can do. I can tackle the B, A, B with this, so I get 0, 0, 0, A, B, B, A, B. And then I do it again, 0, 0, 0, A, B, A, B, B, and 0, 0, 0, A, B, B, B. And so it worked. Oh, I haven't done yet. I'm sorry. We've got to do replacement. So I can start to do replacement using these rules. It'd be 0, 0, 0, 1, A, B, B, B. Eventually we'll get over to the B, 0, 0, 0, 1, 1, 1, 2, B, B, etc. Now this rule BA produces AB is somewhat problematic. It's a very powerful phrase. And then this issue of starting at 0 is difficult for another type of grammar. This would be a type 0 grammar. We'll see that. And this will be a type 1 grammar if I restrict it to n greater than or equal to 1, and I have S producing 0S A B and S producing 0 A B. And then I can replace A produces AB with this. I could go BA produces BX, BX produces YX, YX produces AX, and AX produces AB. So we get the same effect, but the nice thing about this is it's all contextual. Everything that was replaced had context around it. A was replacing X is replacing A only when it's next to B. Y is replacing B only when it's next to X. A is replacing Y only when they're next to X. And then B is replacing X when it's next to A. This is known as a type 1 language. All right, so we'll cover the slide that talks about the different language types in a separate video.